Our next speaker is a bit of a break from tradition in that Robert is from Ramboll ourselves. As an associate, Robert Bamford heads Web Structures, Ramboll's future design studio, developing and promoting cutting-edge parametrics and advanced computational design techniques. Today, he will give us an engineer's perspective on the myriad of tools and techniques which are available to design practitioners, and on how these tools may in fact not just be mere tools, but collaborators. Over to you, Robert.
Thank you, Ruth. It's a pleasure to be here at the inaugural Design Excellence Forum. Today, we'll be looking at some work on design and technology with an engineering focus, and really a journey that we have undertaken studying technology and its application to geometry within structural engineering and other disciplines. To start with, though, I think one of the most interesting aspects of technology is really where the mind's eye sits. And so, rather than technology, we're going to start by looking at the mind's eye through nature. Nature is one of the great proponents of technology, and one of the great designers, the master builder, indeed itself. And so, initially, we're going to take a look at design collaborators that we use in technology and how we are using these tools, these new collaborative tools through computational design to in some way replicate, but also try to reach some of the capabilities that Mother Nature has been doing for a very long time. These maps, or heat maps as we call them, are unfolded elevations of a high-rise building, and this is using a process called topological optimization. Effectively, we're putting material where it works best. This is, of course, one of nature's building blocks, which is to design around using a minimum of material and to maximize freedom of form. So these new processes, which have become sort of more widely available lately, are helping us to define geometry with greater freedom. And these unwrapped elevations were used on this competition. Every trick in the book, almost. There's branching strategies, there's tie strategies, there's catenary and arching going on in all of these things. So rarely does nature, when you give it the freedom, does it decide to go with a straight column or a straight beam. In fact, it avoids right angles and straight lines at every opportunity, electing for more efficient load paths through curvature and branching strategies. This was ultimately the design that we used, which we applied some rationalization to take out some of the complexity of the original topological heat map. But we used a framing strategy so we could stay in fidelity with the suggested load lines through the topological study. So still to replicate the way a structure would grow as if being built by Mother Nature. We also, as we went into the, as we started to develop these geometric strategies, we also carried out a case study on obviously a recent building, 432 Park Avenue in New York, super tall, super skinny, advanced structure, very advanced, highly advanced structure, but obviously very, very orthogonal, very Cartesian, straight lines everywhere, everything's a right angle. And we wanted to investigate what the potential was for applying some of nature's strategies to such a tower. So we applied this process of creating this topological optimization heat map on the facades. We kept all the internal structure identical as per the original design. And then we recreated the framing around the information, the informed heat map, and which we subsequently analyzed and then compared. And what we found was we got this incredible performance enhancement. So we got something like a 2/3 enhancement to the lateral performance of the tower. So it became much stiffer. It also, we created a slight reduction in the structural mass of about 7.5%. So it seems that using nature's strategies, certainly as indicated on this, you can have enhanced performance for less material. So we get greater economy with something that becomes more performative. Obviously, the geometric aspect of this is more complex than the previous design, but such is the advancement. The geometric complexities are things also which are being unlocked through advancements in digital fabrication, additive manufacture, etc. Moving on, and once we started to further investigate and develop our strategies to control geometry, we found a field of design or optimization, or geometric optimization, where we can effectively manipulate geometry and control the geometry using objectives. In this instance, we are going to manipulate the geometry of this building massing, which contains very large cantilevers and also long span elements, just by tweaking the arrangement of the architectural massing. So we're not moving them very much, but it's just to find small geometric changes that provide large structural gains. We are shifting each of these bars, the top left corner just in rotation, top right corner just with a shift in the X direction, etc. And then the bottom right hand corner combining all of these three. And what we find is we can, through small shifts, achieve very, very substantial gain. So in this case, we could reduce the energy of the building, so how hard the structure has to work, by about 1/4. Of course, this will then reflect in how much material needs to go into the design to reduce carbon emissions, etc., as well as reduce cost. We also developed multiple objective optimization strategies in this journey of geometry, and this is 8 Conley in Kuala Lumpur, which will become the world's tallest twisted twin towers. And we used computational design to achieve multiple objectives. So we incorporated, in addition to sort of nature's objectives, we incorporated architectural goals, client goals within this optimization to encourage the twisting of the towers, yet still to enable the balancing of the structures, to allow for even load distribution at the base. So these multiple objective techniques, which often have this best trade-off quality, allow us to find the best mutual solution for these different objectives which are sort of are opposing each other. We also developed techniques and strategies which allowed us to delve deep into form found and very non-linear form found structures. This one is at the smaller end of the scale. This is a sculpture, a paper sculpture in London, and we developed an approach called simulated reality, where we built some test models to assess, or physical test models to assess the real performance of the sculpture, and then we tuned a computational design model to the physical results, resulting in this behavior here. We use this simulation to be able to control this very non-linear form found structure, and then once we had a final settled geometry, we were able to export this and analyze it, and then check the stress at all of the interfaces between these, something like, well, a few thousand paper tetrahedral units or Sonobe units, and to confirm that they could be that we didn't need to glue them together, that they could hold themselves just by friction. other aspects of nature, this time on the larger scale. We've developed strategies that also can inform a structure through, say, Newtonian principles, gravity well processes, but using some sort of physical guide or physical principle to then develop the form finding for a structure. So this is for an airport roof. And we use this principle of gravity well to create these mega funnels to promote arching between the supports to enable a long span, but also subsequently integrate with MEP strategies and the like. So really enabling something that could be defined through a parametric principle or a single principle. So to enable a very simple parametric definition, but also to have underlying structural or engineering intelligence behind it. We're also able to encode in these processes additional layers of intelligence within the form finder. You can see the struts within this are being adjusted based on certain rules. So this sort of form finding approach can also be very complex and develop to become far smarter than sort of single layer deformation techniques. We're effectively optimizing the geometry as we're form finding it. And here was the final result for this. On the smaller scale, we also take inspiration from connectivity as structural engineers, at least. So multi-noded structures. So the neurology or the structural neurology is an area that we've also looked in. So how can we create strategies which encourage multi-noded structures to benefit strength? So effectively to minimize material behavior. We took inspiration from Frei Otto, who carried out these wet wall thread experiments some time ago, and we tried to recreate the spirit and certainly the results using computational design tactics. It's a very sort of long form found nonlinear process, which uses the sort of magnetic attraction or attraction in the same way as the original experiments would. And we're able to recreate this sort of process, which we could then apply, obviously, to far more complex boundary conditions. And in doing so, we developed these forms which have an initial logic to them, but then somewhat develop into almost coral-like structures. Again, something that could be based around or has the appearance of something that's slightly natural. On top of the form found structure, which is sort of minimum energy structure, we can also apply layers of other tactics. In this instance, we're applying a geometric optimization tactic. Minimize the energy. You can see it encourages the curvature of the top branches, and then from there carry out analysis, putting this together into a workflow, and then to post-process those results into a mesh, which then creates this form, and which was used for testing complex 3D printing processes. And what you can see here as we cut the 3D printing planes is that despite the structure being has the appearance in 3D of being very complicated, on plan there's a underlying regularity to all the structure. So it's sort of this ability to encode logic within designs, and to manipulate geometry to find complex but efficient forms. That is the sort of cutting edge, as we see it, of technology. Here we can see some of these forms being 3D printed, a test piece. And this approach, which we developed for a research initiative, we also then we also utilized for other structures and competitions to create pseudo tree-like canopy structures. And you can see on plan these structures have very much the appearance of a sort of branching or leaf-like arrangement. And effectively, these sorts of tools and tactics, we believe, are getting us back a little bit closer to the mind of nature, and effectively to be able to design and reach solutions using modern tools that allow us to get to achieve similar results to how nature would grow a structure. We think is an advancement that, you know, only a few years ago was something that was something that would be impossible. Within this whole process of research, development, applying new tactics, and creating these new concepts and applying technology to them, we develop workflows which enable us to streamline how we approach projects. This is an example of a workflow using, again, computational design as the engine to drive speed, consistency, and using a single geometric platform. So effectively, this sort of digimetric workflow enables us to use geometry or generate geometry on a single platform in Rhino Grasshopper, export that geometry around and import it back so that we can add additional details to the same geometric set, and even within that same platform also create drawings and export to BIM, etc. The time savings in this obviously are very important, but also is the consistency of the data, knowing that we have federated geometric models, analytical models, and ultimately BIM models too. The sort of step beyond this workflow, what we call holographic design, is the ability within the computational design platform to go further into analytics and detailing, so that everything can be handled in a sort of computational design space. And that's what we achieved in this competition. We were able to develop the structure, carry out the analysis, as well as some other aspects, but effectively to create an overall developed structural package, fully coordinated with the architectural geometry at a super early stage. And it's this sort of informative approach to the ability to apply almost construction stage details to concepts, and do so rapidly, so that we can inform the people, clients and architects, about the implications of choices and also possibilities at a time when adjustments can be made to the overall design. And I think, aside from capabilities, the potential for in technology and enabling us to inform decision makers at a super early stage is part and parcel of the development of design at this stage. And so, through the intersection of design with technology, from an engineer's perspective, we are starting to get a glimpse into the mind of nature. Thank you very much.